For rotating vessels, say for example, we have here a cylindrical container which is partially filled with liquid. If the container is rotated at a certain angular velocity, the liquid surface changes and it forms a vortex which is in the shape of paraboloid. So there is an equivalent depth depending on how fast the rotation of the container is. So to determine this depth of this paraboloid that is formed by the liquid surface, we can solve that using this solution. We have y equals to w squared r squared over 2g. W is the angular velocity, which is in rad per second. R is the radius of the cylinder, and g is the acceleration due to gravity. So if we are required to determine the slope at any point within this paraboloid, we can use the solution tan theta equals to w squared x over g. So at any point x, we can determine the slope of the parabola. In other problems, other solutions, we can use the squared property of parabola. So depending on the problem, later on, we can use this squared property of parabola. The volume of paraboloid, this is our solution. We all know that in solid geometry, 1/2 pi r squared h. We have a conversion factor of 1 rpm is equivalent to 1 over 30 pi radian per second. So if the given value for the angular rotation is in rpm, we should convert it to rad per second. So let's discuss the liquid conditions. First, on open vessels. Let's say we have a partially filled open vessel, cylindrical open vessel. So let's say we have a cylindrical container with more than half full of liquid, and it is rotated about its vertical axis. So we have several cases that will happen on the liquid surface of, the fluid depending on how fast the angular speed or angular velocity of the container when it is rotated. So that depth y, when the vortex is formed, so that depth y is distributed equally above its initial liquid level and below its liquid level. So if we have computed y using the formula that I've mentioned earlier, this distance y will be equal above it and below, or it is divided equally where the vertex of the paraboloid starts and where it will end. So here are your endpoints of this paraboloid. So with a total depth of y. So in the first case, if y over 2 or 1/2 of the computed y is less than the depth in which it is the distance of the initial liquid level to the rim of the open vessel, so there will be no liquid spilled on this container when it is rotated. But on the second case, if the 1/2 of the computed y is just equals to the distance d, or the depth from the rim to the initial liquid level, so the liquid surface will just touch the top rim of the container, where there will be no liquid that will be spilled on these containers still. So, but if the angular rotation increases again, so the value of y is very high. That's why the computed y over 2 could be greater than the distance d. So what will happen here is that uh, water will be spilled and the liquid surface will still have a depth of paraboloid which is equivalent to y. Again, the liquid surface will just follow this distance y that is computed using the formula. So uh, the computed y will remain, and we will start measuring the distance y from the rim up to this point. So liquid will be spilled on this condition if y over 2 is greater than d. Another condition is that if y is equals to h. So the computed y is equals to the total depth of the container. So it means that the vertex of the paraboloid will just touch the bottom portion of this cylinder. Of course, there will be liquid that will be spilled on this container. Okay? And the last, if the computed y exceeds the depth of the container, so it means that if we are going to draw the paraboloid again, we will touch at the top. We will start at the top rim and we will extend that below the bottom portion of the container, where we have here an imaginary paraboloid, the imaginary part of the paraboloid, which is at the bottom of this container. So this will be the shape of the paraboloid that will be formed here on this container when y is greater than h. Again, in this scenario, liquid will be spilled. So on our sample problems, we will solve how we will compute the volume of water that will be spilled and other scenarios with regards to the rotating vessels. So let's try solving some problems.
So here's an example. We have an open cylindrical tank, 2 meters in diameter. So this is 2 meters. Uh, and it is 5 meters high. It contains water to a depth of 4 meters. It is rotated about its own vertical axis. Okay, with a constant angular speed W. What is the depth of the vortex by the liquid surface at 3 rad per second? Is there any liquid spilled? So let's answer letter A. So let's just have a copy of this figure to solve letter A. So to solve A, uh, let's determine first this distance from the rim to the liquid surface. So if the total depth of the containers is 5 and the depth of fluid is 4, we have 1 meter. Okay. Then to identify if there will be water spilled, let's solve first the depth of the vortex of the liquid surface when it is rotated. So let's assume that this will be your vortex. Okay. So we can confirm that there is no water spilled on this container when it is rotated at 3 rad per second. So W 3 rad per second. If this depth of vortex y, so when we have a paraboloid, so that depth is distributed equally uh, from the liquid surface above and below. So that's y over 2. So if y over 2 is less than this depth right here, which is 1 meter, so we can say that there will be no water spill because y over 2 will not exceed the this distance from the rim to the liquid surface. So let's solve first y. Y has a formula which is equals to W squared R squared over 2G. So what y equals to W should be in rad per second. So rad per second already. We can directly substitute that. Raised to 2. The radius is, if we have 2-meter diameter, the radius is half of it. R squared is divided by 2 times G, which is 9.81 meter per second squared. So the units will be cancelled out. The unit will be in meter. So we have 3 squared times 1 squared. Sorry. 3 squared multiplied by 1 squared is just 1 divided by 2 times 9.81. Okay, W squared R squared over 2G. So the answer for y is 0.459. Okay, if we round off to the third decimal place. 0.459, and when we divide it by 2, let's say 0.459 divided by 2 is 0.229 or 0.2295 meters. Okay, so the answer for letter A is 0.459, and we can confirm that there will be no water spilled when y over 2, which is equals to 0.2295, is less than this distance d, which is 1 meter. Okay, so this is less than d, which is equals to 1 meter. Therefore, no water is spilled. Okay, so here are your answers for letter A. Okay, for letter B, what maximum value of W in RPM, revolutions per minute, can be imposed without spilling any liquid? Okay, so what will be the angular velocity? So let's say here for letter B. Okay. For letter B, the goal here is to determine the W in order for us to have a vortex that will end on the rim without spilling any liquid. Okay, so the liquid surface will just touch the rim, okay, without spilling any liquid. So in order for us to determine this W, uh, we have to determine the Y. That should be equals to twice the distance d. Okay, so for the second case from the slides, the y over 2, or the half of this depth of the vortex or of the paraboloid, should be equals to d. Okay, so let's determine d, and we already have a value for d, which is 1 meter. So it means if y over 2 is equals to 1 meter, y should be multiply both sides by 2. That's 2 meters. So if we have a 2 meter value of y, we can determine now the angular velocity. Using the formula again, y equals to w squared r squared over 2g. So w is required. So let's determine w. Okay, let's isolate w. Multiply both sides by 2g over r squared first. To cancel out this. So we have 2gy over r squared equals to w squared. Take the square root of both sides. Okay, so we have the square root of 2gy over r squared equals to w. Okay, or vice versa, we have 2gy over r squared. Substitute the given. We have 2 times g, 9.81 meter per second squared. Y should be 2 meters. That's 2 meters divided by r squared. The radius is 1 meter. So 1 meter squared. The W will be in rad per second. Okay. Square root of 2 times 9.81 multiplied by 2 divided by 1 squared. Okay. So W is 6.264 rad per second. But the required answer should be in RPM. Okay. So let's convert this to radius per minute. Revolutions per minute, sorry. So to convert 6.264 rad per second, okay, we have a conversion factor of 1 RPM is equivalent to pi over 30 rad per second. So canceled out the unit. W is equals to 6.264 multiplied by 1 over pi over 30. That's 59.817 revolutions per minute. Okay, that's your W. Letter C. If W is 8 rad per second, how much water is spilled out, and to what depth will the water stand when brought to rest? Okay, so let's determine the volume of water that will be spilled. So let's have a copy of this figure again for letter C. Okay, so it is rotated at 8 rad per second. Okay, so 8 rad per second. This is 8 rad per second. So we can confirm that this is the maximum W, which is in rad per second, 6.264, for it to have the vortex or the liquid surface to touch the rim without spilling. Since our W is greater than 6.264, it is expected that um, our computed Y will be greater than or the 1/2 of y will be greater than this depth 1 meter. So there will be water spilled. So how do we determine the volume that will be spilled on this container when it is rotated at 8 rad per second? For letter C, let's solve again y, which has a formula of w squared r squared over 2g. So y equals to w 8 rad per second squared, r is 1 meter squared divided by 2g, 9.81 meter per second squared. Okay, y is in meters. We have 8 squared by 1 squared divided by 2g, 3.262. That's your y. Okay, so 1/2 of 3.262 is greater than 1. Okay, 3.262 is 1.631. So it will exceed the rim. So since we have y of 3.262, so instead of attaining this vortex or this liquid surface, some volume of water will be spilled. So what we will do is that the liquid surface will just follow this value y, which is measured from the rim. Okay, so from the rim we have a value of y of 3.262. So we'll just measure 3.262 from the rim going down. So let's say that 3.262 is right here. Okay, then we draw the paraboloid. Okay, so this will be your liquid surface. Okay, has a depth of y equals to 3.262 meters. So one way to solve this is that we can use this volume of air within this open container. Okay, if this is the new volume of air, which will be greater than its original volume of air, we can now compare or determine the change in the volume of air in this container. So initially we have the volume of air, which is this one in the shape of cylinder. Okay, let's determine that the volume of air before it is rotated. So if this is 1 meter, the volume of the cylinder will be pi r squared, which is 1 meter squared, multiplied by its height, which is also 1 meter. Okay, pi r squared h, volume of cylinder. So pi times 1 squared times 1 is just equals to pi. Okay, or 3.1416 cubic meters. That's the volume of air before. How about the volume after? So in order for us to determine the volume after it is rotated, this will be your volume, which is volume of the paraboloid. Okay? So volume of paraboloid, which is also volume of air after it is rotated. Okay. We can use the solution, which is equals to 1/2 pi r squared h. So 1/2 pi radius of this paraboloid should be the radius of this cylinder also, which is 1 meter. Okay, 1 meter squared. H is the total depth. Y equals to 3.262. Okay, so this H here in this formula is your Y, computed Y. Okay, so the volume of the paraboloid, or the air, volume of the air after it is rotated, is equals to, okay, 1/2 is 0.5 by pi r squared h, 3.262. Okay, the answer is 5.124. 5.124 cubic meters. So this is your new volume of the air in the open container. So it means the volume of the air increases. So that volume of air occupied the water. Okay, that is spilled on the container. So what we will do here is just we will subtract the volume of uh, the paraboloid, or the air after it is rotated, by the volume of air before it is rotated, for us to determine the volume of water that is spilled. Okay, so volume of air after minus volume of air before it is rotated. So that's 5.124 cubic meters minus 3.1416 cubic meters. So the volume of water spilled is equals to 5.124 minus 3.1416, okay, 1.982 cubic meters. This is your answer for letter C. For letter D, what angular speed in RPM will the depth of water at the center of the tank be 0? So here on letter C, 3.262 is less than the total depth, which is 5 meters. So the vortex will just reach in between this container. But in letter D, we are required to determine the angular speed, which is in RPM, for the depth of water, or for the liquid surface, to reach the bottom of this container. So again, let's copy this figure. And for letter D, let's put it here. For letter D, okay, so the vortex should touch the bottom. Okay, so the vertex of our paraboloid should be at the bottom. Okay, so this is paraboloid. So it means, sorry, the figure should be like this because there will be water spilled. Okay, so it should be like this. Okay, so what will be the W here? In order for the vortex to reach the bottom of the container. Okay, of course there will be liquid that will be spilled because the angular speed should be stronger than this angular speed on letter C in order for it to reach the bottom of the container. Okay, so it means the depth of this vortex should be your Y, computed Y, and it should be equals to the depth of the container, which is 5 meters. So Using again the solution y equals to w squared r squared over 2g, we already have y, so we will be able to compute w. So let's use again the same derivation of the solution here in letter B. If we have a given y, we can determine w. So let's use this, the square root of 2gy over r squared. Okay. Square root of 2gy over r squared. So w is equals to the square root of 2 times 9.81 meter per second squared. Y is 5 meters over r squared, which is radius is 1 meter. So 1 meter squared. W is equals to square root of 2 times 9.81 by 5 over 1 squared. So the answer is 9.9045. 9045. That's in rad per second. Again, let's convert this to revolutions per minute because it is required there. 1 RPM is divided by pi over 30 rad per second. So W is equals to, say, 9.9045 divided by uh, pi over 30. 94. Okay. 94.581 revolutions per minute. Okay. So any angular velocity exceeding this value, or in rad per second, which is 9.9045, um, the the vortex will now be greater than the depth of the container. But here, for letter D, this will be your angular speed in order for the liquid surface to reach the bottom of the tank. Okay? For So that's letter D. For letter E, if W is equals to 120 RPM, how much area at the bottom of the tank is uncovered? So we have 120 uh, revolutions per minute. Okay, so for letter E, so 120 is greater than 94.581. So uh, that's the case number 5 on the slides earlier. So it means that if we are going to draw the figure of the liquid surface, okay, so it will exceed the bottom portion of our cylindrical tank. So again, the depth of the paraboloid should be measured from the rim. Okay, it will be always measured from the rim always for open containers. So we expect that it is greater. Okay, the computed y will be greater than the total depth of this container. Okay, this is your y. Y over 2, or y is greater than the depth of the container, which is 5 meters. So if we have W, which is 120 RPM, let's convert that first to rad per second. To convert that, just multiply pi over 30. Okay, so 120 multiplied by pi over 30. 12.566 rad per second. Okay, this is 1 rad. W equals to 12.566. Then we use again the solution y equals to W squared R squared over 2G. So W is 12.566 rad per second squared. R is 1 meter. 1 meter square over 2G. 2 times 9.81 meter per second square. Okay, Y is now computed. 12.566 squared multiplied by 1 squared. Sorry. Squared over 2G. Okay, the answer is 8.048. 8.048 meters. So that's your total depth. This is 8.048 meters. Okay, so what is required in this problem is how much area of the bottom of the tank is uncovered. So it means if our vortex exceeds the total depth of the tank, so it means this area right here where the the liquid surface touches the bottom portion of this tank will be uncovered. Okay, so there's no water here. Okay, which is in the shape also of circle. So how do we determine this area of this uncovered portion? Okay, uncovered portion of the bottom of the tank. So it means this is your liquid right here. Okay, the sides. Okay, so how do we determine this area? So what we can use here is we use squared property of parabola. So let's say this is your radius, which is 1 meter. Let's say this is distance x, and we assign this as y1 because we have a total depth of y. Okay, so we equate the ratio of the depth of the paraboloid with respect to its equivalent radius, okay, or the horizontal distance, and we take the square of it. So using squared property of parabola, okay, squared property of parabola, we have uh, we take the square of the radius over its depth, which is the computed y. We equate that to the smaller parabola because this will be your bigger parabola, which is this one, r squared over y, and our smaller parabola will be this one. Okay, so we take the smaller radius, which is x. Okay, that's x squared, and its depth, which is this distance right here. We can determine y1 by simply subtracting the computed y by the total depth of the container. So y1 equals to uh, y minus 5 meters. So 8.048 minus 5 meters, y1 is 3.048 meters. Okay, so we determine here x. Okay, that distance x will serve as the radius of the circle that is uncovered on the bottom part of this container. Okay, so let's determine x. We multiply both sides by y1. We have y1 r squared over y equals to x squared. Take the square root of both sides. We have the square root of y1 r squared over y equals to x. Okay, substitute now. We have, let's just change the arrangement. We put x on the left side. We have y1 is 3.048 meters multiplied by r squared, or the radius, which is 1. Take the square, and divided by y, which is the computed y, 8.048. Okay, 8.048 meters. So x is equals to square root of 3.048 multiplied by 1 is square divided by 8.048. Okay, the answer is 0.615 meters. So x is 0.615. Then we can now compute the area of this circle. Okay, so the area uncovered is equals to pi r squared, or pi x squared. So pi times 0.615 meters square. So the area is pi times 0.615 square, 1.188 square meter. That's the answer for letter E. Okay, so going back to letter A, if the problem requires to determine the maximum and minimum pressure acting at the bottom of the tank, what we will just do here is that the minimum pressure on the tank will be at the center because it has the least depth of fluid. On the other hand, the maximum pressure on the tank will be on the sides, okay, because the depth of fluid will be greater. Okay, so let's say we will determine here on this problem in letter A the minimum and maximum pressure at the bottom. So we will just determine here the depth. Okay, so the depth of the fluid. So for the minimum pressure, uh, the pressure is just computed by the product of the unit weight and the pressure head, or the depth of the fluid. So the minimum pressure is at the center. Let's just determine this depth. Okay, so what will be this distance? If this is y over 2, we will just subtract 4 meters by y over 2 in order for us to determine this distance. Let's say h1. Okay, so let's say this is h1. For h1, we will just subtract 4 meters by y over 2. h1 is equals to 4 meters minus 0.2295. h1 is equals to 4 minus 0.2295, 3.7705 meters. So we can now determine the pressure minimum, which is 9.81 kilonewtons per cubic meter multiplied by 3.7705 meters. So the minimum pressure is 36.988 kilopascal. That's what the answer will be, kilonewtons per square meter. Next, maximum pressure. Okay, the depth of the fluid will be this one. Okay, so it is just the sum of the initial depth of water, which is 4 meter, and y over 2. Okay? Y over 2 since the depth of the vortex is distributed equally at the top and the bottom portion. Okay? So it's also y over 2. So let's say this is H2. Let's determine H2. H2 is 4 meters plus y over 2 or 4 meters plus 0.2295. So H2 is 4.2295 meters, and therefore the maximum pressure is just the product again of the unit weight and the depth, 9.81 kilonewtons per cubic meter multiplied by 4.2295 meters. So the maximum pressure is 9.81 by 4.2295, 41.491 kilopascal. So this is your answer here for maximum pressure, the bottom of the tank. Okay?